Good morning students. Today we will discuss about free electron theory of metals. Now, what are free electrons? Free electrons means these are the valency electrons. Now, where does valency electrons exist? Valency electrons exist in outermost orbitals of the atoms. So, why these valency electrons are important? Why these outermost electrons are important means it can give the electrical properties. It can give the electrical properties. It not only gives the electrical properties for metals, it can also discusses about non-metals. Next, it can explain about electrical, thermal and magnetic properties of all types of solids. Now, this free electron theory was developed in three stages. So, first one is classical free electron theory. So, first one is classical free electron theory. Next, second one is quantum free electron theory. Next, third one is zone theory or band theory of solids. Okay. First, if we go for first one, the classical free electron theory. Classical free electron theory. This classical free electron theory was developed by Drude and Lorentz. So that's why it is also called as Drude-Lorentz theory. This classical free electron theory is also called as Drude and Lorentz theory. It was developed in 1900. Here, according to this theory, the metal contains free electrons. These obey classical laws. So, here electrons obey classical laws. Next, here electrons move in a constant potential. Means, see here in a metal, the electrons will be moving all over the metal. So, here the electron will be moving in constant potential. Means, everywhere the potential will be the same. In this whole metal, everywhere the potential will be the same. So, this is about classical free electron theory. So, this is developed by Drude and Lorentz. According to this theory, electrons obey classical mechanics and electrons move in constant potential. Next, second one is quantum free electron theory. This quantum free electron theory was developed by Sommerfeld. According to this theory, electrons obey quantum laws. Here, according to quantum theory, free electrons obey quantum laws. Next, here also electron move in constant potential. Electrons will be moving in the constant potential. So, this quantum free electron theory, it is also called as Sommerfeld theory because it is developed by Sommerfeld. Next one is the zone theory or band theory of solids. Now, this zone theory or band theory of solids was first developed by scientist named Bloch. Bloch, Bloch. So, here according to this theory, electron will be moving in periodic potential. So, see here, according to this theory, electrons will be moving in periodic potential. Means potential is not constant, it varies. It varies. It may be maximum at some place, it may be minimum at some place, or otherwise it will be maximum at some place, it can be zero at some place, but it is repeated. So, it varies periodically. Here, these electrons obey quantum mechanics. So, these electrons obey quantum laws. And this theory is also, see here, the zone theory is also called as band theory of solids. So, free electron theory was developed in three stages. One is classical free electron theory. Next one is quantum free electron theory. Next one is zone theory. Now, we'll discuss about classical free electron theory of metals. We'll be discussing about classical free electron theory of metals. Now, see here, what are the postulates of classical free electron theory? So, the postulates of classical free electron theory means the assumptions of classical free electron theory. So, first assumption is, see here, atoms revolve around the nucleus. We know that atoms will be revolving around the, means electrons will be moving around the nucleus. In atom, electrons will be revolving around the nucleus. So, metal is consisting of like these atoms. So, metal consists of like these atoms. Next, here next assumption is here electrons are free to move. Means electrons will be moving freely in the metal. So, they are considered as, these electrons are considered as molecules in a gas. How molecules will be moving in a gas? Like that only, here electrons also moving in a metal. So, electrons in the metal are considered as molecules in a gas. Next assumption is, here these free electrons move in random directions. So, see here the electrons will be moving in random directions. So, what happens? Here it consists of a metal. Now, this metal consists of atoms. These atoms loses free electrons. When atom loses free electrons, what does they become? Positive ions. So what happens when the electron is moving in a metal? These electrons may collide with electrons, other electrons, and these electrons may collide with positive ions. So what happens in a metal? When electrons comes out of the atom becomes positive ion. So the electrons and positive ions. When electron is moving freely throughout the metal, what happens? This electron may collide with another electron. This electron may collide with positive ion. But these electron-electron collisions and electron-positive ion collisions are neglected. So see here, these electrons move in random directions and collide with either positive ions fixed to the lattice or other free electrons. All collisions are elastic and these are neglected. These are not considered in this classical theory. Next, see here, the movement of free electrons obey kinetic theory of gases because free electrons are considered as molecules in a gas. That's why they thought that these free electrons obey kinetic theory of gases. Means how molecules are treated in a gas, like that only same laws we are applying for electrons in a metal. This is another assumption. Next, the electron velocities obey classical Maxwell-Boltzmann distribution of velocities. Means see here the electrons, how electrons are arranged in different states. So see here how electrons are arranged in different states, whether 2 electrons can sit or 1 electron can sit, whether all the electrons can sit in single state. So that restriction is given by Maxwell-Boltzmann distribution. So how electrons are distributed in different states, that is given by Maxwell-Boltzmann distribution. So here electrons obey Maxwell-Boltzmann distribution. Next, free electrons move in uniform potential field, means it moves in constant potential. Electrons will be moving in constant potential. Next, when you apply electric field, so see here what happens, the electrons will be moving in a direction opposite to electric field. So electrons will be moving in a direction. If electric field is in this direction, the electrons will be moving opposite to the electric field. So these are the assumptions made by classical free electron theory. Okay, but classical theory is a big failure. It was unable to explain many aspects due to these assumptions. Due to these assumptions, it was unable to explain many aspects. And they thought that next one is all free electrons. All free electrons means valency electrons. All valency electrons are conduction electrons. They thought that all valency electrons are conduction electrons. Means all free electrons can be responsible for conduction. That is also another assumption. So some assumptions are true, but many assumptions are false. That's why it is a big failure. Okay, now we'll see the success of classical free electron theory, means merits of classical free electron theory. Okay, now what are the merits of classical free electron theory? It can verify Ohm's law. So V is equal to IR, it can verify. Next, it can derive Weidmann-French law, means it gives the relation between thermal conductivity and electrical conductivity. So thermal conductivity sigma T divided by electrical conductivity sigma E is directly proportional to T. This law is given by classical free electron theory. Next, it can explain about electrical and thermal conductivities of metals. Means it can explain only about metals. But what about semiconductors and insulators? It cannot explain. It can explain only about metals. Next, it explains optical properties of metal. It can explain the optical properties of metals. So it can discuss only about metals, that is also electrical, thermal and optical properties. So these are the merits of classical free electron theory. Now, if we go for demerits or drawbacks of classical free electron theory. Okay, in the drawbacks, see here it fails to explain the electrical conductivity of semiconductors and insulators. It can give only electrical conductivity of metals, but it cannot give semiconductors and insulators. Next, it failed to explain the temperature variation of electrical conductivity at low temperatures. So see here, it cannot give electrical conductivity, how it varies at low temperatures. Next, see here, the concept of specific heat of metals cannot be explained by classical free electron theory. Next, it failed to explain the mean free path of electrons. Next, it was unable to explain about photoelectric effect, Compton effect, black body radiation. All these cannot be explained. Next, it failed to explain temperature dependence of paramagnetic susceptibility and ferromagnetism. How temperature means how susceptibility varies with respect to temperature. In paramagnetic materials and ferromagnetic materials, it cannot give. Next failure is, see here we said that all free electrons are valency electrons. Means if valency electrons are more, its conductivity should be more. Okay, but see here for aluminum valency electrons are more. For copper valency electrons are only 2 valency electrons, but for aluminum 3 valency electrons. According to classical mechanics, which should be the good conductor? Aluminum should be the good conductor. But practically which one is good conductor? Copper is good conductor. So this cannot be explained by classical laws. Okay, so all these experimental verifications cannot be explained by classical mechanics. So these can be modified with the help of quantum free electron theory. This quantum free electron theory, we also call it as Sommerfeld theory. Okay, now, so see here, due to postulates, classical postulates, it is a big failure. Now, it was modified by Sommerfeld. So, according to Sommerfeld, the assumptions are, the postulates are, see here, the free electrons in a metal can have only discrete energies. So here the metal will be having discrete energy levels. Here energy is not continuous, it is energy is discrete and energies are quantized. We have seen En is equal to particle in potential was n square h square by 8 ml square. So energy is quantized and it has discrete energy levels. Next, according to quantum mechanics, the electrons obey Pauli's exclusion principle. Pauli's exclusion principle means no two electrons can be in single state. See here, if two electrons exist in one state, they should be of opposite spins. That is given by Pauli's exclusion principle. Next, the distribution of electrons in various levels obey Fermi-Dirac distribution. Means previously we have seen that the distribution of electrons obey Maxwell-Boltzmann distribution. But here distribution of electrons obey Fermi-Dirac distribution. So see here we are having two distributions, Bose-Einstein and Fermi-Dirac. But electron is having spin half. Half integral spin particles obey Fermi-Dirac. If it is photon, if it is spin 1, 0, 1, 2, 3, all these spins obey Bose-Einstein. Half 3 by 2, 5 by 2, half integral spins obey Fermi-Dirac. So electron is having spin half, it obey Fermi-Dirac distribution function. Next, here potential energy means the electrons, free electrons will be moving in a constant potential. It will be moving in a constant potential. As usual, like classical mechanics, it will be moving in a constant potential. Next, here also, when electron is moving, it may collide with other electrons and it may collide with positive ions. So here electron lattice ion and electron-electron collisions can be neglected. Next, here electrons are treated as wave-like particles, means moving particle exhibits wave nature. So here electrons exhibit wave-like properties. Okay. Now these are the assumptions of quantum free electron theory. So quantum free electron theory was able to explain all the drawbacks of classical free electron theory, but it failed in very few aspects. Okay. Now we'll see merits of quantum free electron theory. So see here, all the demerits of classical mechanics was explained by quantum free electron theory. So it can explain about electrical and thermal conductivities of metals, and it can also explain about electrical and thermal conductivities of semiconductors. It can explain about not only metals, it can explain about semiconductors, and it can also explain about insulators. Okay. Next, it can explain the ionic phenomenon. Next, it can explain temperature dependence of conductivity of metals. So see here, when temperature increases, what happens to conductivity in metals? What happens? Conductivity decreases. Why decreases? Why decreases means due to collisions. Due to collisions it decreases. Okay. So when electrons collide, what happens? Its conductivity decreases, resistivity increases. So this can be explained by quantum free electron theory. Next, it can explain about specific heats, and it can explain about magnetic susceptibilities for paramagnetic materials, ferromagnetic materials, and it can be able to explain about photoelectric effect, Compton effect, and black body radiation. Next, it can give the correct mathematical relation for thermal conductivities of metals. Okay, these are the merits of quantum free electron theory. Next, what are the failures of demerits of quantum free electron theory? So see here, there are some demerits for quantum free electron theory also. In spite of explaining many drawbacks of classical free electron theory, this is also having demerits. That's why band theory was introduced. Okay. So see here, demerits. It is unable to explain metallic properties exhibited by certain crystals. So some crystals are there. Few crystals are there. For those few crystals, it cannot give metallic properties. For example, quartz crystal, calcite crystal. For them, it was unable to give metallic properties. Next, it is unable to explain why metallic crystals means, see here, it is unable to explain why atomic errors in metallic crystals should prefer certain structures only. So see here, why certain metals are having only certain structures, why not other structures? It cannot be explained by quantum free electron theory. Next, the big failure of quantum free electron theory is it cannot give the differentiation between metals, semiconductors and insulators. On what basis solids are divided into metals, semiconductors and insulators? Depending on band gap, depending on forbidden band gap. But according to quantum mechanics, there are discrete energy levels, no bands. This cannot be explained by quantum free electron theory. Next, it failed to explain the positive value of Hall coefficient. For Hall coefficient, why positive value? That cannot be explained. Next, according to this theory, only 2 electrons are present in the Fermi level and they are responsible for conduction, which is not true. So here they are saying that the highest occupied level, 2 electrons, Why these are responsible for the conduction? This cannot be explained. So these are the demerits of quantum free electron theory. Okay, all these demerits are explained by third one, zone theory or band theory of solids, which is stated by Bloch, scientist name Bloch. So this we will discuss in the later classes. Thank you.